Okay, this video is going to be about quantum mechanics and atomic orbitals, and it's going to be a lot about me just sort of like reading through the notes and what's actually important for you to know from this information. So in the last section, we talked about the fact that we can't see where electrons are at any point because they're moving too fast and because they're super tiny, okay? So this guy Schrodinger comes along and he developed this big, long, calculus-related equation to demonstrate both the wave-like and particle behavior that an electron has. Because we have to remember that light doesn't have mass or take up space. So it's not matter, okay? So it's kind of really hard to describe how an electron moves like something that doesn't take up space like an electron does, okay? So an electron is funny in one of those senses that it can have matter-like properties and non-matter-like properties, and that is the wavelength and the particle behavior. So he developed this thing called quantum mechanics, which is physical chemistry, which you won't do until your senior year of college if you decided to go on with chemistry, because there's tons and tons of calculus involved in that. It's one of my favorites, highly recommend it. Okay, but what it allows us to do is to talk about the probability that an electron will be in a given space, okay? So let's talk about electron density. Electron density is where the electron could possibly be. So you'll notice that this is sort of like fuzzy on the outside and really dark on the inside, okay? So we don't want to say that an electron can't be out here, but we're going to say that it's going to be closer to where the two atoms are connected, okay? Which is how we illustrate it most of the time in chemistry, is just by drawing a big circle for an atom. Okay, orbitals and quantum numbers. So orbitals have wave functions corresponding to a certain energy level, okay? And then that gives us a specific electron density for a shape of an orbital. So you may remember our orbitals as S, P, D, etc. Okay, so that's what that is. The orbital relates based off of what Schrodinger said to a wave function of an electron, which is just a fancy way of saying this is where the electron could possibly be. Okay, so Bohr, if we go back to what we talked about with Bohr gave us the idea of energy to describe in like an orbit, okay? But quantum mechanics give us more of a space, okay? An area of where it could be. So that's all that you have to know for quantum mechanics and atomic orbitals, is that electron density tells us that this is the space where an electron could possibly be. So how do we represent these orbitals though? Okay, so this is taking us back to when you took honors chemistry, which is the spaces in which we're going to describe the orbitals, okay? So the first one is an s orbital. So it's spherically symmetrical. It's the same distance from the nucleus regardless of where you are, which is basically the definition of a sphere. And it has a radial probability function, which is the probability that you will see those electrons from that distance from the nucleus. So kind of like what I was showing you up here, okay? So if this is your sphere, technically the electrons could be anywhere within that sphere, okay? So if you look here, you have different nodes. So this is showing us, this would be for a 1s, okay, so hydrogen, helium. There's only one space where those electrons can be located. Where when we go to 2s, you now have a space where those two nodes are connected. Okay, and so there's zero probability that those electrons will be in that space. So here's your 1s, and then here's your 2s. And then for a 3s, you have two nodes where your electrons can't be. Okay? You also have your p orbital, which is the, so let's just refresh our memories. The s orbitals are the groups 1 and 2. Okay, where our p orbitals are our groups 13 through 18. Okay, this is where electrons are concentrated into 2 region, which we know them as the dumbbell orbital. Okay, and in this case, the node is going to be where those 2 orbitals are, or where the dumbbell or the middle of the dumbbell region is. Okay, which is the nucleus of the atom. And then the last two orbitals that we have are D and F. These are way too confusing to discuss. We used to have shape for a D orbital, but we don't really know, and by we, I mean chemists don't really know if that's really the shape anymore. And the F orbitals, we're really not even sure what their shapes are. So you're not expected to know those two shapes, okay? And then the last thing I'm going to talk about are many electrons. So just basically anything besides hydrogen, okay? So the presence of more than one electron changes the energies of the orbitals, okay? A given value of an orbital will increase with energy. So 3s has less energy than 3p has less energy than 3d. And then degenerate are orbitals within the same energy. So all three of these would be considered degenerate orbitals, okay, because they're all in that 3 energy level. And there's two other things that we have to think about, which is the electron spin. Okay, so an electron spins on its horizontal axis. So the electron actually spins like this instead of like what you're used to with like the Earth. Okay, so an electron spins on the horizontal axis. Okay, and the Pauli exclusion says that no two electrons in an atom can spin in the same direction. So one atom would have to spin like this, and the other one would have to spin backwards, okay? And we'll do some examples where we'll notice that you'll have to illustrate this when you do orbital notations. Great, thank you.